Hi guys, and welcome to preliminary chemistry topic number 3, water. And this is video number 3 on the properties of water. We're going to deal with some of the explanations for the relationship between the structure and bonding in water and its properties in a later video. But for now, we're just going to have a look at a couple of the key properties of water and some of the things that may affect those. What we know is that at room temperature, which is expected to sort of be around about 25 degrees C, that water is a liquid. Water exists as a liquid, and that's the most common form in which it exists on planet Earth. We also know from previous video that water is a polar molecule. That is, water has a positive and a negative region. The negative region is where the oxygen atom is, and the positive region is where the two hydrogen atoms are, and that's because the electrons in the shared bond are closer to the oxygen because of its electronegativity, and therefore there is a polarity of a dipole created as a negative and a positive for this molecule. As a consequence, it's able to dissolve ionic solids, salts with anions and cations. It can also dissolve polar molecular compounds, certainly small ones and particular types of ones, and it's also colorless. But in addition to these properties, there's a couple of other important ones which we might have a little bit of a look at in this video. The first of these is density. One of the interesting things about water is that for most substances, when you cool them, you remove energy from the particles. And so because they don't tend to have as much energy, they don't move as fast, and they tend to pack closer and closer together. So generally speaking, most substances actually become more tightly packed and therefore become denser as they cool. Now, water does this to a certain extent, but it gets to a point where it will actually, around about 4 degrees, start to expand as it cools. And as a consequence, solid water, or ice, is actually less dense than liquid water. It would be the case for most substances, if you were able to drop their solid form into their liquid form, that it would sink. But water isn't like that. For water, when you put the solid form into the liquid form, it actually floats. It's less dense than its liquid. If we remember that density is equal to mass divided by volume, then for a given mass, which must remain constant, the relationship then must occur between density and volume. So if we've got a certain amount of mass being packed into different amounts of space, that would account for the density. Now, generally speaking, if the volume is smaller, that is, if we can pack that mass into a smaller volume, then as the volume goes down, the density goes up. So therefore, to explain the observation that water is less dense, that means if density has gone down, then it follows that volume must go up. So as water is cooling, its little molecules actually start to get slightly further apart and take up more space. This is unusual, and it can be explained a little bit by the diagram that I have here. If you can track this individual molecule, you'll notice that around this individual water molecule are four other water molecules in the form of a tetrahedron. And that's the shape that you can see here drawn. The tetrahedral arrangement is what gives the crystal of ice as it forms that sort of six-fold structure, I guess, in a sense. It also means that each individual oxygen is actually surrounded by four hydrogens. Two of these are bonded hydrogens, so they are covalently bonded, and the other two, so this one and this one, are held together by what we call hydrogen bonds. We have talked briefly about hydrogen bonds, but we'll go into them in a little bit more detail later in this topic. So we've got physical bonds, the hydrogen bonds, and chemical bonds, the covalent bonds, that are holding this whole structure together. But clearly there are weak spots as we look at this. So the two keys that we need to be aware of as we're looking at these changes is, firstly, each oxygen atom is surrounded by 4 hydrogen atoms, and the water molecules are arranged in a tetrahedral arrangement, both the organization around that oxygen and also for each water molecule. When the ice is melting, the water molecules will actually gain energy. But as they gain energy, the crystalline structure will disappear, and actually the molecules will start to become a little bit closer together for a little while. Closer molecules equals lower volume, and this equals higher density. Two other properties that we'll look at very briefly are melting point and boiling point. The interesting things about melting and boiling point, which kind of carry on from what we just talked about in the transition from ice to water, is that the melting point of water can actually be changed. Depending on whether we're going from the solid to the liquid, or in this case, the liquid to the solid, and therefore we are freezing, the point at which that occurs can actually be changed by the addition of a solute. Certain different types of salts can be added to water, and they will actually change the water's properties, its melting point and its boiling point. One of the things we know is that salt water, for example, will freeze at a lower temperature than pure water. The impurities created disrupt the consistent organization of the crystals, and as a consequence of that, salt, if we think about salt as being sodium ions and chloride ions that are present within the crystal structure, upset that crystal structure and change how the solid forms. Boiling point can also be changed, and there's a lot of points on this particular slide, but let's just try and get things, understand things generally. The melting point of water is 0 degrees C, that's the MP. The boiling point, the BP, is 100 degrees. Now we just said there's certain things that we can add to change the melting point. Well, we can also change the boiling point too. If the air pressure rises, then the boiling point will also rise. Likewise, if the air pressure drops or if the air becomes thinner, less molecules, then the boiling point will also drop. One of the things that we know is that if you have water at great depths, and hydrothermal water, then it can reach very high temperatures, perhaps as much as 260 degrees, and still remain a liquid. But as that water starts to rise towards the surface, the pressure starts to drop, and that reduction in pressure allows those molecules to start to move further apart from one another, which is our definition of a gas, and then often that can happen very rapidly. And so the process of change from liquid to gas is happening so rapidly that we get the formation of a geyser. Water can also boil at temperatures below 100 degrees, which I just mentioned, and places where that may happen include high altitudes, and it's about the pressure being lower than sea level or the air just being thinner, carrying less molecules. So how do we explain the effects of antifreeze on water in a radiator? Well, in the radiator, there are two important things that you're looking for. The first thing you're looking for is a reduction in the temperature of the freezing temperature of the water, and that's about 8 degrees. And usually that occurs with about a 20% concentration of ethylene glycol or antifreeze. So you need a reasonable amount in your radiator if you're going to drop the freezing temperature down to -8 degrees. And for a lot of places, -8 isn't too bad. Temperature doesn't usually get that low, so the water can remain still a liquid in the radiator and you don't have problems with it expanding and cracking your radiator. The antifreeze can also increase the boiling point too by several degrees, and that can also act as a preventative in slowing down the rate at which the water is going to boil. Thanks for watching.